Welcome back. In today's lecture, we will learn the classical dimensional analysis as a technique of obtaining similarity rules. The premise of dimensional analysis is that the form of any physically significant equation must be such that the relationship between the actual physical quantities remains valid independent of the magnitude of the base units. So, if the relationship between the actual physical quantities remain valid independent of magnitude of base units, that means the equation must be dimensionally homogeneous. Suppose we are interested in some particular physical quantity Q naught that is a dependent variable or a dependent parameter in a well-defined physical process or event. I will do an example. In the theory of elasticity, deformations are denoted as large if the relationship between stress and deformation is no longer linear. In your first course in strength of materials or properties of materials, you had done relations where the equation between stress and deformation is linear. That is valid only for what are termed as small deformations. So let's do an example where deformations are large. This is, for example, the case for the geometric nonlinearity arising due to large deformation, as for example, occurring in a fishing rod. The first and most important step in dimensional analysis is to identify a complete set of independent quantities, Q1, Q2 to Qn, that determine the value of Q naught, so that we could write Q naught as a function of Q1, Q2, etc. In the example, we seek the deformation delta of the elastic rod under the influence of a single force P applied at the end of the rod and forcing of it under its own weight. The general relationship between the deformation delta and the length L and the cross area A of the rod, the force P that we apply, and the modulus of elasticity E, the density rho of the rod material, and the gravitational acceleration G, is then of the form delta is a function of P, the force, L, the length, A, the area of cross section, rho, the density, G, acceleration due to gravity, and E, the elasticity, the elastic modulus of the rod material. Thus, the value of n here is 6. There are 6 independent parameters that are there in the problem. We have to determine the dependent parameter delta, the deflection at the end of the rod. The next step is to choose a system of units, MLT, FLT, or even FMLT, as we discussed in the last class. Let's choose the MLT system. Write down the dimensions of all the variables and parameters, dependent and independent, in terms of the dimensions of the base quantities. So we have this table here. The first column lists the variables and parameters, in this case only the parameters, and then the dimension of mass, the dimension of length, and the dimension of time, MLT. Delta, the deflection, obviously has only the dimension of length. P, the force, is mass times acceleration. So it has a dimension of m1, L1, t minus 2. Similarly, the dimension of the other quantities. E, the elasticity, is like stress per unit strain. So it has a dimension of stress, which is force divided by area. So the dimensions are mass 1, length minus 1, and t minus 2. We now pick from the complete set of physically independent variables and parameters, in our case only the parameters, Q1, Q2 to Qn, a complete and dimensionally independent subset, Q1, Q2, qk with k less than n. So it is a subset of q1 to qn, k less than equal to n. Dimensionally independent, what does that mean? A subset q1, q2, qk of the set q1 to qn is dimensionally independent if none of its member has a dimension that can be expressed in terms of dimension of the remaining members. We'll explain this with example. Complete. The subset is complete if the dimension of all the remaining quantities qk plus 1, qk plus 2, qn, that is beyond qk, of the full set can be expressed in terms of the dimension of the subset q1, q2, qk only. In an example, the complete set of independent variables and parameters is P, L, A, rho, G, and E. From this, we choose a subset of 3 quantities. Since we are dealing with MLT system, with these 3 base quantities, this subset can have only 3 quantities. 3 quantities can provide you a complete and dimensionally independent subset. If we choose 4, then most probably the 4th quantity will not be dimensionally independent of the other 3. Let they be L, G, and E, denoted in yellow tint. In this table, notice that these 3 quantities form a complete subset in the sense that we can express the dimension m from these 3. In these 3, we can make a algebraic combination, a multiplicative combination, such that the dimension of that group would only be mass. Similarly, we could have a combination which has a dimension only of length. For example, L, the length of the rod has dimension L. And similarly, we can formulate a system which has a dimension only of time. Since equation for Q naught is dimensionally homogeneous, the dimension of the dependent variable Q naught is also expressible in terms of dimension Q1, Q2 to Qk, the subset. So the 3 parameters that we have chosen in the basic group, L, G, and E. The dimension of L is simply L, of G is L t minus 2, the acceleration, and of E is like stress, M L minus 1 t minus 2. Now, having chosen a complete dimensionally independent subset, we express the dimension of Q naught and the remaining quantities k plus 1 to Qn in terms of the dimension of Q1, Q2, Qk. Thus, they will have the form Qi is equal to Q1 raised to power n I1, Q2 raised to power n I2, and similarly Qk raised to power n Ik. So in our example, we would have delta would have a dimension of L raised to power alpha, G raised to power beta, and E raised to power gamma. After taking out the variable L, G, and E, the remaining variables are delta, P, A, and rho, which we have written on the left-hand column at the end. We express Qi as L raised to power Ni plus 1, G raised to power Ni2, and E raised to power Nik for each of the remaining variables. Delta obviously would have simply the dimension L, so it can be written as L alpha is equal to 1, beta is equal to 0, so G 0 and E 0. So delta would have the same dimension as L. P, on the other hand, has a dimension M L minus 1 T minus 2. And we want to represent it as L raised to power alpha, G raised to power beta, E raised to power gamma. So M L minus 1 t minus 2 would become L raised to power alpha. We substitute the dimension of G, L t minus 2, L t minus 2 raised to power beta, and we substitute the dimension of E, M L minus 1 t minus 2 raised to power gamma. Now, dimensional homogeneity requires that the value of alpha should be 2. We can write the equation. Dimension of M would mean that M on the left hand side should be equal to, on the right hand side, M raised to power gamma. So gamma must be 1. Now let's look at the dimension of T. T is minus 2 on the left hand side. On the right hand side is minus 2 beta, minus 2 gamma. Minus 2 beta from the dimension of G and minus 2 gamma from the dimension of E. So minus 2 on the left hand side power of T should be equal to minus 2 beta minus 2 gamma. Since gamma is 1 determined already, beta must be 0. Similarly, we get alpha is equal to 2. So P has the same dimension as L square E. So we write the value of alpha as 2, write the value of beta is 0, and of gamma as 1 as a second line in this table against P. Similarly, area has a dimension, two-dimensional length, and so it can be simply write 2, 0, 0. And the density rho can be written as L minus 1, G minus 1, and E raised to power 1. Verify this would have the same dimension as that of density, M L raised to power minus 3. So, the next step is defining dimensionless forms of the n minus k remaining independent variables by dividing each one of the product of the powers of q1, q2, qa, which has the same dimension. So qi is qk plus i divided by the powers of qki, which was q1 raised to power ni1, q2 raised to power ni2, and k raised to power nik. So that if this is what we had calculated earlier, then clearly against delta, we can write delta divided by L would be dimensionless, because delta has a dimension of L. So delta by L would be dimensionless. Similarly, P has a dimension L square times E. So P divided by L square E is dimensionless. A has a dimension L square. So A L square is dimensionless. Similarly, rho was shown to have the dimension L raised to minus 1, G raised to minus 1, E raised to power 1. That is rho G L divided by E is dimensionless. Actually, it's rho divided by E divided by LG, which simplifies to rho GL by E. So this factor delta by L, shown with a red background, dependent parameter, non-dimensional dependent parameter in terms of the basic group, is a function of three non-dimensional parameters: P divided by L square E, A divided by L square, and rho GL divided by E. This is how we can organize our calculations in this table. And this, then we can write pi naught, the dependent non-dimensional parameters in terms of the basic group, which in our case is delta by L, is a function of pi 1 to pi n k. The values of the dimensionless quantity are independent of the sizes of the base units. The value of q1 to qk, on the other hand, do depend on base unit size. They cannot be put into dimensionless form since they are by definition dimensionally independent of each other. Therefore, pi naught can be written as function of pi 1 to pi n minus k. So, if out of n basic quantities, independent uniquity parameters, we need k to form the basic group, then n minus k pi's would be formed. N minus k non-dimensional groups of parameters would be formed. And pi naught, the dependent non-dimensional parameter, would be a function of these n minus k non-dimensional pi's. So we can write delta by L is a function of P divided by L square E, A by L square, and rho G L by E. When a complete relationship between dimensionless physical quantities expressed in dimensionless form, the number of independent quantities that appear in it is reduced from the original n to n minus k, where k is the maximum number original n that were dimensionally independent. A rigorous proof of this theorem, which is known as the Buckingham Pi-theorem, can be found in this reference. Bridgman is another reference where you can find the proof. So this is the form of the deflection of the fishing rod that we have determined. Notice that originally there were 6 independent parameters. Now the number of independent pi's is only 3, 6 minus 3, where k, the number of basic groups, is 3. This change of the functional relationship between delta and the 6 independent parameters has now changed into a functional relationship between delta by L and 3 independent groups of non-dimensional parameters. This decrease from 6 to 3 represent a substantial advantage to the researcher, to the person solving the problem. We can construct scale models. Modeling rules. When we make scale models, all we have to ensure for similarity is that the values of these 3 non-dimensional groups match between models and prototype. Thus, the first group, P divided by L square E, must have the same value in the model as in the prototype. Similarly, rho G L by E, the value of this in the model must match the value of this in the prototype. A by L square in the model should match A by L square in the prototype. This is an easier order than matching all the 6 quantities independently, because then it will not be a model at all, it will be the prototype itself. So reduction in the numbers of matching parameters, in the number of parameters that are required to be matched, results in substantial convenience to the researcher. And once we do this, once these 3 parameters have matching values in model and prototype, then the dependent parameter delta by L in the prototype would have the same value as in the model. Thus, we can construct a scale model, and this scale model, if we measure delta by L, the value of delta by L of the prototype would be exactly the same value as you obtained in the model. So if we could measure the value of delta in the model, we could predict the value of delta in the prototype. This is what a major use of dimensional analysis is. It permits us to do scale model tests. Thank you.